So now for the addition reactions, and now we're going to just synthesize alcohols in this presentation. So everything has OH in it, or whatever we synthesize. Here are all your reactions again that I gave you before in the addition reactions. The green check marks are the ones that we have already done. So we've done 4 reactions in the previous PowerPoint, and now we're going to go ahead with the rest, not rest of them, but the alcohol ones. Okay, so wherever you see an alcohol, that's going to be covered here, and I know you don't see alcohol here, but it's there. I'll show you. Okay, so that's going to be here. Okay, moving on. So a review for the mechanisms that we have learned already from the previous presentation for alkene addition is that alkenes are the nucleophiles. The reagent is generally going to be your electrophile. The alkenes are different kinds, symmetric, asymmetric, terminal, or internal, because this kind of an alkene will determine whether you're going to have Markovnikov addition or, so you get one product, two products, how many do you get? Whether your addition is going to be on the same side or anti-side, that's not dependent on the alkene type. That is dependent on the mechanism, okay, of the reaction. And then mechanism also leads to rearrangements. Wherever there is a carbocation, you will have rearrangement, okay? So that is definitely all there. Nothing has changed in that. So then we can continue on. So hydration is going to be an addition reaction, just like normal. Only thing here is that we are making alcohol. So in all of these slides, you will find only synthesis for alcohols. Definitely different kinds of reagents. That's why I made this separately. So there are different kinds of hydrations. There are different kinds of reagents we are going to use. Again, you can make Markovnikov product. You can make a single alcohol. You can make a diol. So everything we are going to learn over here, whatever you want to make will determine what kind of reagent you're going to use. Okay, obviously. All right. So, all of these reagents that we are going to learn here are going to be important. Now, I just want to clarify one thing before I move ahead is that I'm going to try to do the mechanism for all of them as much as possible. But if I don't do a mechanism, then generally I don't ask you also to write the mechanism for me. Okay. And also as a disclaimer, wherever there is a carbocation, I will give you the mechanism, and I will ask you also to give me the mechanism for those, because carbocations are kind of, very important intermediates in organic. Okay. All right, so first of all, addition of water with acid catalyst. Now, water itself is not a strong enough electrophile, okay, even though we're talking about alkene, which is electron rich. Water by itself is not going to do anything to alkene, so you have to add acid as a catalyst. When you add acid as a catalyst, then you end up getting H3O plus, which now is a nice electrophile. Okay, so here's what we do is you take an alkene and then you add water to it. Again, small amount of acid. What acid do we use? Sulfuric acid, a little bit phosphoric acid. Either of them or both of them will do this. And so once you do that, then you end up getting these two alcohols. Okay, so again here, look at this alkene. This alkene is a symmetric alkene. So it's very similar to what we did with HBr before, where we were adding, hydrobromic acid. So the bromine can go on either of these two carbon because this is an internal alkene and it is symmetrical alkene. Again, let me remind you what symmetrical means is that on this carbon, you have a carbon and a hydrogen, and on this carbon, you have a carbon and a hydrogen. Okay, so the double bond is important, the 1, 2. So that's why you end up getting two products in this case. And you also get two products because the alkene is asymmetric in the sense that you have different groups over here. Okay, so it's symmetric also in the sense that you have a carbon and a hydrogen, but you get two products because the alkyl groups on both sides of the double bond are different. Okay, if it was the same, if it was 2-butene, we would just get the one product. Okay, so that's one way to avoid getting multiple products, by the way. Okay, is that you choose an alkene that is symmetrical. But anyway, in this case, I just wanted to show you that there is no specificity as to where the OH is going because the alkene, the double bond here, is the same. Okay, whether you go to this carbon or that carbon. Okay, So then here, if we have a terminal alkene, so here again is the, two different kind of products you can get, the Markovnikov product and the anti-Markovnikov. Markovnikov again is where the hydrogen goes to the carbon with more hydrogen, and that is the only product you get, okay, for alkene, for alcohol. And this is again because of the carbocation mechanism. Okay, so which means we need to just kind of go over the mechanism a little bit. This mechanism, by the way, just to give you a disclaimer again, that's very similar to the HBr addition or HCl. So it's very similar. If you know that, you know this as well. So let's look at the mechanism. Here is the double bond attacking the acid proton. So once it gets the proton over here, that hydrogen now goes to the carbon with more hydrogen, this Markovnikov. Why is it that? Because the secondary carbocation is more stable, right? If you were to form carbocation here, that's less stable. So once that happens, then the water will attack, and this is the main difference between the hydrobromide addition and this addition, because once you have water attacking, you have the oxonium ion over here. So remember, those two H's are still there, so which means that you need the water to come in and pick up this extra proton to give the alcohol. This is the mechanism. You cannot skip any steps in this kind of a reaction. The other thing I want you to note over here is the equilibrium arrows, because if you remember from what we did before with dehydration, is you can use acid to dehydrate alcohols to give you alkenes. Okay, so the concentration of the acid is going to determine whether your reaction is going forward or backward. If you have a lot of water, you're doing hydration. If you have a lot of acid, you're going backward. Okay, so it depends on that. So usually when you want to do hydration, you want to make an alcohol, you want to keep it fairly dilute, okay, and just a little bit of acid in there. So anyhow, this is the mechanism, and just kind of remind you again, okay, when you add water, please don't get rid of any of the hydrogens until the water will come and pick up the hydrogen from here. And again, don't use anything that I have not given you. So which means I'm saying is don't use hydroxides or ethoxide, methoxide, any of that stuff. So because we have a carbocation, we are also going to have rearrangements, right? So that's kind of a normal thing to do. So again, if you look at this one and if you look back at the HBr, I gave you the same mechanism or the same starting material because it's the same thing. So I don't want you to think that I'm teaching you something new here, something you have done multiple times before. So this product just shows you this will never ever form, because once you form the carbocation, the OH, the hydride will shift over here to give you the more stable carbocation. So the water will never attack this carbocation. So which means this will never ever form, okay, if you have this kind of a starting material. So the shift is going to happen. You will form the tertiary carbocation, and then the water will attack, and then you will deprotonate the oxonium ion, okay, to give this kind of an alcohol. So you will never get this, not even as a minor product, okay, so don't go there. And here is another one for rearrangement. So this one, again, just another example here for you, okay. So here I showed you one more thing though, okay. So here, look at what's happening. So here you have this kind of an alkene, cycloalkene. It doesn't really matter which kind of an alkene. So, but anyhow, the main thing is that there is rearrangement possible. So you will form this carbocation, okay, over here. Now, I wrote over here that this one will not form, right? Because when you pick up a hydrogen, in this case, the alkene looks like symmetrical, right? So you have one hydrogen here, and then the carbon here and a carbon here. But in this case, it's not as symmetrical in the sense that if you make a carbocation here, then you can get a methyl shift to get a more stable carbocation. So this kind of a cation will never form, okay, which means that, this cation is the only one that's formed, because you have the double bond, so you can form the cation either on carbon number 1, carbon number 2. But if you form on carbon number 2, there is no rearrangement possible. there is no more stability of carbocation, okay? And so therefore only one of these intermediates is going to form, all right? And there's nothing you can do, just follow that, okay? So don't give this one at all. And also once you form this cation, again remember, water will not attack this carbocation only after you have rearranged the carbocation, or once you've rearranged the methyl group, then only you will have the water attacking, okay? And again, you don't have to write the methyl shift. I wrote it, but you don't have to. If you want to, you can, okay, just for yourself, because then, you know, kind of helps you out. The second reaction we are learning here is oxymercuration. So why do we have this one? So you saw in the previous slide, we got rearrangements because of the carbocation mechanism, right? So sometimes you don't want that, right? So you want to make a very specific kind of a product without having to bother with the rearrangement stuff, right? So you don't want that, and so you use what's called oxymercuration, in which the reagent is this, which is mercury diacetate. The THF here is the solvent, okay? Then you use this in presence of water. That is the one that provides the OH. And then the 2 here tells you this is the workup, okay? So for every reaction, generally for every synthesis that you do, you have a reagent and then you have a workup. We generally have not been talking about workup so far because our workups have been just washing with water, and I never even mentioned that, okay? Because this is more theory, you learn that more in the lab, okay? But I need to kind of mention this now so you understand what the 2 is. You will not put these two together, okay? So which means that when you're writing your reagent, okay, and you're writing Hg, you know, OAC2, THF you want to write or you don't want to write, but you're not going to write comma NaBH4, for example. You're never going to do this part, okay? So you have to do 1 and 2. So that tells you that you're adding these two things separately and not together, okay? So all the one that you're all adding together, and then the bottom part you're adding after 1 hour, 2 hours, or whatever you decide, you know, that your reaction is done. And that's what research is for, right? So you figure out how long it takes for you to do the reaction. Anyhow, so the mercury diacetate, first let me explain this to you about the OAC group. The OAC group here is called the acyl group. And AC is the short form for acyl, just like we have Me as short form for methyl. So what happens is that the acyl group here is just the CH3 C double bond O. This is the acyl group, okay? And then if you remember, let me just show you this, okay? So it kind of makes sense to you. This is the acetic acid. This is the acyl group. The OAC, that is the acetate, okay? So OAC is the acetate, all right? So it's just a short form of writing acetate because the AC is just this part, all right? So you can look this over and see if that helps you again. If not, let me know. I can explain a little bit more to you, okay? So here, what are we doing? Our reagent is mercury diacetate, and then once we use this, we get Markovnikov product. So that has not changed, okay? That we're still getting Markovnikov product. But now once you do the reaction with this kind of an alkene, remember I just showed you in the previous slide that if you take this one and use water with acid as catalyst, you're going to end up getting rearrangement. But in this case, you don't get rearrangement. You do get the two products, okay? Because there is no rearrangement. So both of these carbons now are equivalent, sort of. And so you will get two products. Now you can avoid that if you want to. That's a different thing, okay? But you will get two products, okay? And you will not get rearrangement. And that's a major thing, okay? To not get rearrangement. Now, I don't usually ask you the mechanism for this, so I'm not really showing you the mechanism. If you want to look at the mechanism, go for it, okay? It's in the textbook, or you can find it online as well, okay? But I'm not covering it. All right, And then we have hydroboration. Now, what's hydroboration about? Hydroboration is when you need an anti-Markovnikov product. Okay, so until now, we've been talking about Markovnikov product, which is the hydrogen goes to the carbon with more hydrogen. But what if you don't want that? Okay, so for example, when you have this kind of an alkene, this is the third time you're seeing this now. So this alkene now with the hydroboration will give you alcohol on the terminal carbon and the hydrogen goes in the middle. Okay, so that's kind of what happens. It's completely reversed now. All right, and hydroboration is an extremely common kind of a reagent to use for making alcohols because it works beautifully. What is the reagent? The reagent is right here. Okay, so it's BH3. This dot that you see here, that's the lone pair of electron, and that's THF. What is THF? So let me show you. I mean, I've given you the structure, I think, a long time ago, back when we were doing solvents, but THF is this structure, tetrahydrofuran. Okay, so this is that's the furan. So what happens is that the BH3, if you remember again from your acids and bases, it's in group number 3. So it's like a Lewis acid. So if it's a Lewis acid, it's also in complete valence shell. All right. So it needs something to stabilize. And so it shares these electrons with the oxygen. So the THF is not really reacting with BH3, is just stabilizing it. That's all. Okay, because when you need to order reagents from whichever chemical company, it needs to be stabilized, otherwise they will not ship it, right? So in any case, so that's what the THF is for. Now, if you can see the color coding, I know it's kind of light over here. So the hydrogen for the alcohol, that's coming from the H, okay, of the BH3. All right, so this is that H, and then the workup, now you understand the workup part. So this is a second step now. So once you have, done the reaction with this, again, whatever 2 hours, 3 hours that you need to complete the reaction, then you add hydrogen peroxide in presence of a base like sodium hydroxide or something, and then this will provide the OH. Okay, so in this one, I do need to talk a little bit about the mechanism, because you need to understand why this is happening. Markovnikov, you understood, okay, because hydrogen goes to the carbon with more hydrogen and so on. So what happens with the BH3 is that this is the kind of intermediate you get, okay? So the hydrogen actually goes to the carbon that is more substituted. Okay, it does not go to the carbon with more hydrogen. Why? Because you have the boron, and boron needs a little bit more space. So because of steric issues, the hydrogen goes to the carbon that is more substituted. Okay, that's what happens. Now, the other thing I want to just mention here slightly, and again, we haven't talked about this before, is mole ratios, right? Because I've never said anything about how much of a reagent you need, because generally, so far, all the reagents we've been needing, they've been in excess. Okay, so I never mentioned this before. And here also, generally, you can use the borane in excess because it's not an expensive reagent. Okay, but when you're using expensive reagents, you want to make sure that you have the right mole ratio so you don't waste any reagent. But the thing about the borane is that because it has 3 hydrogens, the ratio of the reagent to the substrate is 1:3. Okay, because there are 3 hydrogens that it can combine with, which even makes it even more sterically hindered. Okay, because now you have another hydrogen that will be with another cyclopentane and another hydrogen with another cyclopentane. So it's getting sterically crowded here. So that's kind of what happened. And once you have all of those 3 bonded, that's when then you add the hydrogen peroxide, because at that point the reaction is over. Okay, and again, how long does it take you to do that depends on your research, right? And you have figured that out by monitoring the reaction. So it can take you half an hour or 2 hours, whatever it needs. Once you wash it with hydrogen peroxide, then you end up getting your alcohol, which is now the anti-Markovnikov product. Okay, so very straightforward kind of a reaction, very nice and neat reaction. So we have done 3 alcohol reactions now. Okay. Now the next one that we have is what is called the halohydrin formation, and in this case you're adding a halogen along with the water, okay, which means that you're adding an OH also, okay, over here. So in this case, here is your starting material, and I've taken an asymmetric alkene because I need to show you what happens and where things are adding. So here is a Cl2, here is water, so you add them together, and this is the solvent. Okay, now you can put the solvent here also. I just put it down here so it's easier for you to understand, but otherwise you have these two as the reagent, and look what's happening over here. The OH is going to the carbon that is more substituted, so which means Cl is starting the reaction. So it's kind of like a Markovnikov sort of an addition, okay? There's no hydrogen, but if you were to pretend that this was hydrogen, then chlorine is going to the carbon with more hydrogen, okay? That's kind of what's happening. So it's sort of a Markovnikov thing. Now, the other aspect of this reaction is that it is an anti-addition. You can see I've shown you the stereochemistry. So let's look at the mechanism just slightly over here. And I think you should know this mechanism because we've been encountering anti-additions for a while, and we will encounter more also. Okay, so it's a good idea to know this mechanism. So here is what's happening. Here you have an alkene. This adds to the chlorine. So you remember we have done this reaction before when we added the halogen to an alkene, but now in this case we also have water. So when we need to open up this chloronium ion, then the water will attack instead of the chlorine. Okay, so now the water is going to attack this carbon right here. Chlorine goes to the carbon with more hydrogens. Okay, remember Markovnikov addition. We will talk a little bit more about why this happens in another chapter, because you might think, and I hope I'm not confusing you, you can close your ears if you don't want to listen to this or forward me, but if you think about it, this water is actually going to the carbon that is more sterically hindered, right? So why does this happen? And this is really happening a little bit more because this carbon is kind of behaving like a carbocation. So this is the more stable carbocation, all right, because this kind of an addition is more like a carbocation mechanism, all right? So it's not like an SN2, because if you think of it as SN2, then you'll think like, why is it attacking here? It should attack here. But water does attack on this side, and then it's attacking from the back side because the front side is occupied with the chloronium ion, so it attacks from the back side. Okay, and again, right now, if you don't want to remember the carbocation mechanism, that's totally fine. Just remember it as a Markovnikov addition. Okay, so I've written it here also. And then don't forget that once you add water, you also have to deprotonate that in order to get OH. And I really encourage you to learn this mechanism because you will encounter this again, as I said. Okay, so two things here, Markovnikov addition and anti-addition. And by the way, you can do this with bromine also. We don't work with fluorine or iodine in these cases. All right, and now we have what's called diol formation, diol meaning two alcohols. So here I'm going to show you the syn addition, okay? So yeah, which means that anti-addition is also coming, but in any case, this one is the syn addition. So in a syn addition, you have things adding on the same side, okay? So we've done syn addition before with hydrogenation, okay? So we are going to be using two different reagents over here. They're kind of similar, but they're different, definitely. Osmium tetroxide, OSO4. If you look at osmium, yeah, you probably have to hunt for it on the periodic table. It is a transition metal, okay, way down from iron. Okay, so it has the same kind of bonding as iron, but in any case, because it's a heavy metal, it behaves very differently. So osmium tetroxide, and then again, remember 1 and 2. So 1 is the reagent, 2nd is the workup. And so you end up getting a syn addition like this. So I've shown you a very brief kind of a mechanism, okay, as to why this is happening. And that's because when you have osmium with the 4 oxygens, the oxygens will attach onto the double bond on the same side. So once you're cleaving and getting rid of the osmium, whatever is remaining of it, then the OH groups are then on the same side. Okay, so this is a syn addition. Now you can do the same thing with potassium permanganate also in cold conditions. Okay, and I've written this as a qual test, so we'll talk about that. But in cold conditions, KMnO4 will work the same way and give you a syn addition as well. And you can see how similar these two are, right, in their intermediates. And then you can wash it up with water and then get the syn diol. Again, oxygen, alcohol groups on the same side. Okay, so what is happening over here versus here? Well, nothing much is different except for the cost of the reaction. Osmium tetroxide is extremely expensive. As I said, it's a heavy metal, so it's really expensive. The other thing about osmium tetroxide is that it's very toxic as well. It vaporizes and gives out fumes that are really, really bad for you. And so it's much better to not work with osmium tetroxide. On the other hand, if you're doing small time thing, small reactions in which you need good yields, then it's really good to work with because it's a very neat kind of a reagent. Okay, so there's no mess or fuss with it. KMnO4, on the other hand, potassium permanganate, we might have seen in the lab already. It's a purple liquid. It's really messy, to work with. And also it's very dark, so it stains, but it's not toxic at least, right? So that's a good thing. But in any case, you choose what you want, and KMnO4 is dirt cheap, so you can easily get KMnO4. So it depends, okay, which lab you work in and what kind of reagents you need, what kind of workup you're, willing to have with this. Because one of the other things that happens with KMnO4, and that's the qual test also with this, is that if you add an alkene to KMnO4, well, you get the diol, right? So it's kind of like an oxidation, right? Because you're adding oxygen, which means that the oxygen is coming from the reagent. Here also, the oxygen is coming from the reagent. Well, then something is getting reduced. What is getting reduced is the reagent. So in this case, and I'm explaining this one because this is a qual test, you end up getting also MnO2. Okay, so MnO2 is a side product, which actually is a solid. So that's a precipitate that forms, and it's a brown colored precipitate. So which means that you can very easily use it as a qual test to know if you have an alkene or not, because when you add it, you get a precipitate and a color change, okay, because the purple is not going to be there anymore. The other thing that's important with this is this has to be done at room temperature at RT, because with heat you can change the kind of products you will get. Okay, so again, you have to be careful, but otherwise this reaction works really beautifully, and a lot of scientists, actually chemists, would prefer to use osmium tetroxide because it's a really nice and neat and clean reagent. So provided you can buy it and you have safe conditions to work in, this is much better to work with. Okay, but again, syn addition, okay, you get, and it's a diol. Okay, so now for the anti-addition. Okay, we just finished the syn addition. So what if you don't want the alcohols on the same side? If you want them on the opposite side, then it's a two-step process. Okay, it's not, you can't do it in one step, and you need very specific reagents. Okay, so let me go over this with you first, and then we'll talk a little bit more here. Okay, so here is the alkene, and the reagent you're going to use here is MCPBA first, and then second, you're going to do acid hydrolysis. And that gives you this kind of a diol, and see the stereochemistry is going in the anti-direction or opposite directions. Okay, so what the heck is MCPBA? First of all, MCPBA is right here, the structure of it, and the name is right here. It is metachloroperbenzoic acid. Okay, so metachloro, and then per means many. Okay, so just like you have water and then you have hydrogen peroxide, so the per actually means that you have more oxygen, or the maximum number of oxygen you can handle. Okay, so here also the per is for an extra oxygen that you have in the acid. Remember, carboxylic acids are 2 oxygens, so the per acid means that you have one more. Okay, so here this is MCPBA, and right now, you know, it doesn't, this is the only per acid we are going to learn for now. Later on, you're going to do this again. Okay, so we're going to learn more, but for right now, just MCPBA is fine. Capital M is fine, small m is fine. Whatever you want to do is okay, provided you write MCPBA, okay, because that's the first thing you need to do. And what does that do? MCPBA will actually give you an epoxide, okay. An epoxide is an ether. It's a very specific ether, which is a 3-membered ring, okay. And you know, because we have to still learn about ethers in the future, that's why this is going to come up again. So in any case, you make an epoxide, and once that epoxide is made, then the second step is that you treat it with acid water. This is called acid hydrolysis. So acid hydrolysis then is going to give you this diol. And this is anti-addition. So in this case, I think it's not going to matter, but you will also get an enantiomer, okay, depending on, this is, I think, symmetrical, so it's okay, but otherwise you will also get an enantiomer, okay. I will write that later on over here, because whenever you have, actually, you know, I shouldn't have to write it. Please understand, okay, wherever I show you any stereochemistry that's forming, you are going to get an enantiomer there, okay. So here, and previous one also with the syn addition, you will get an enantiomer. So in any case, the main thing over here is that, sorry, and this one should be anti. So it should be an anti-addition, and this is the only way right now that you know that you can make anti, okay. And the syn was in the previous slide, and this is how you can make anti. I am not covering the mechanism over here, because when we get to epoxides, that's when I'm going to go ahead and do the mechanism, okay. Right now, just know the reagent. One last thing I want to mention before we kind of are done. We are done with all the alcohol groups, okay, at this point, is the location of groups, okay, that we talk about. So we've talked about the syn and the anti, right, that we already know about. But the one that I want to mention here is about this kind of, you know, chlorine addition or OH addition that we've been talking about, which is a 1,2 addition. Right? So when you added chlorine to a double bond, you got a 1,2 addition, and now you saw the syn and anti addition of diol, and that was also a 1,2 addition. This relationship of a 1,2 is called vicinal. The relationship, if you have the 2 chlorines or the 2 OHs on the same carbon, is called geminal. Just the fact that we have names for these kind of relationships tells you that this is kind of an important thing, because you will encounter them again, okay, on how these groups are added, okay. So it's just a small thing, and again, I know, you know, more words for you to learn, but you know, that's what we're here for. So vicinal, and then geminal, and then if you want shorthand for it, because you know we got shorthands, right, so it's Vic and Gem. Okay, you can use small g, that's fine, okay, but Vic and Gem, those are the shorthand for vicinal and geminal relationships. So that's it, I think, about alcohols, making alcohols. So all these different ways that you can make alcohols. Let me know if you have any questions.